Hello, technicians, and welcome back to the Life Safety Troubleshooter. My name is Gary, and in this video, I would like to delve into basically Life Safety 101. The basics for you new guys, you FNGs, you cubbies. And if you don't know what FNG or cubby is referring to, you might want to ask a senior technician because you probably should be here if you don't know those terms. So the first thing I want to talk about as far as Life Safety 101 is what you need to work on life safety systems. One of the most critical things is knowledge. Make sure you learn Ohm's law. Read the instruction manuals. Find out what it does, how it does it, what its current draw is. The more information you have, the better off you will be. So you want to make sure that you do that. Now we're going to go into what you should be utilizing or what you should have to start being an installer technician. I was a service technician for many, many years, not so much an installer. So I was the one that had to go out and fix something that was broke, misinstalled. They didn't read the instructions properly. They put too many devices out there, yada, yada, yada. So what I want to do first is go ahead and let's switch over to this screen. You can see that I've got several devices here. The blue one is just a meter. It's a nice little meter. It does fine. The red one is what I used normally to do my troubleshooting, simply because it's cheap, it's effective. We're not doing rocket science. We're not building a spacecraft to go to Mars. It's just not what we do. So as long as that multimeter to me would read microamps, I was gold. I was good. That's what I used. So in order to use that meter, and I would read voltage and stuff with that, but I always used a Cobb box too. Now, I developed this over 20 years ago. You should have seen the diagrams to make one of these. It's just a very simple device. Nice and basically small device. Fits in the palm of your hand. So beats carrying around 2 7-amp hour batteries hooked up with a resistor. It's very portable. I did use meter leads made out of what's called tripwire. Now, tripwire is a very old type of wire. I don't even think they make it anymore because the reason it's called tripwire is because it used to be used for security burglar alarm systems. And basically, you would string this wire across the path. It was black. In the dark, you wouldn't see it. And you would literally walk by and pop this wire loose from a ball and pin configuration. It'd pop the wire loose, break a circuit, boom, you'd set off the burglar alarm. Well, the thing inherent about tripwire is it's extremely durable. You can tie this stuff in knots and it will not break. It's made from very, very fine copper stranded wire. Doubt if you'll ever find it anymore, but hey, if you find some trap wire, I would definitely buy it. Nowadays, they use basically regular red and black lead wire. Fairly durable. I've really never had too many of these break except at the connections. But I do use that for lead wire. Another critical device that you want to have, and this is just a very small oscilloscope. It's very cheap. A lot of the stuff I get is off of Amazon. This cost me about $40, I think it was. And the only thing you're looking for with this oscilloscope, and as most of you know, is a lot of these systems are now addressable. So it's important that you be able to look at the SLC, signaling line circuit loop, in order to determine sometimes what your problem is. Now, when you look at that with an oscilloscope, you'll notice you'll see 24, 5, and 0. And I'll go over that in another episode when I get into more technical stuff. But you're able to see what's going on with your SLC loop with that. And able to see if at the end of the circuit, do I really have 24 volts at the end of this circuit, or do I have something that's causing a bit of a problem? So the other meter I would like to show you is I've used a Mushi meter for about 10 or more years. When they first came out, it's a nice little meter. It's an oscilloscope. It's a graphing meter. It will do amps, volts, continuity, ohms. Now, I can't find these anymore, but apparently someone either bought out the patent or they rebranded it, because I found it. I finally found, with the help of a buddy, the N2 Neuron meter, which is basically, it's a different app, but it's basically the Mushi meter. Now, these things come from Amazon, and I bought the one you saw previously here, but they come in a pouch, just like the one you saw, with good, nice set of meter leads, because it allows you to do voltage and current simultaneously, which a lot of my technicians do when they're checking on SLC loops. Because they'll basically put one of these things on the front of the circuit in order to see what's going on. And you can see they've got a video on there, and I'm not going to play all that because you can watch that. For some reason, they advertise this more as a car tool. But seriously, this is what I've used for years. So anyway, they're available at Amazon. They're $219.50. A little bit more. My first Mushi meter I bought like 10 years ago was $125. They did have one Mushi meter left, or a couple left on Amazon. And I think they all got bought out when I told some of you technicians about where to get them. The Mushi meters just kind of, boom, they were gone. So this is it. Mushi meter has a different app. I know I can't use this app to look at this, so I have to use the old Mushi app. And my company's got like 20 of these things. And now they're starting to buy these, because this is basically the same as the Mushi meter. But I would highly recommend you go on Amazon and look for the N2 Neuron and get them while you can. I mean, even if you only get one of them to start out with, you put this thing and you take it and you put it on your SLC circuit going out there into the field, and you've got multiple smokes, modules, smokes, heats, duct detectors, modules. You got all that out there, and you go ahead and break your circuit. Doesn't matter which side you break, as long as you're in series with the devices in the field, and you go ahead and put your N2 on there. You can watch what current draws in here, and you can actually leave it on the site, have it log. It's got a chip in it that records everything that happens, that you can export to an Excel file, and you can graph it like you've seen in some of my previous videos, and it will help you to determine what the problem is. Always the first step of troubleshooting. What is the problem? Do you have a short? Do you have an open? Do you have ramping current draw? Do you have sudden current draw? Do you have a short? Always determine what the problem is before you proceed. Never assume, because we all know what they say about assume. Not good for you or me. We'll leave it at that. Now, the other thing that you want to make sure that you have some very simple tools. This is basically all I used to carry for the most part. I mean, some people like carrying bags. Some people like carrying tool belts. For a long, long time, I used a tool belt. And I would have a straight slot screwdriver, a Phillips, pair of dikes. Now, these are dikes, diagonal cutters. Then wire strippers. There's a couple different wire strippers here. I bought these out of curiosity. I like this one. It folds up. It will do different things with Romex and whatnot. So I do like this. I do like this one. But normally I use this, some screwdrivers like this. You can get these white ones just cheap as can be. Anytime you go to a show or anything, they give them away like candy. You don't mind their advertisement being on there. I used to collect those things like crazy. I think I got a whole drawer of them. But I'd also use a 10-in-1 screwdriver. Came in handy. It had the nut driver on it, and it had the Phillips, the straight slot, the square drive, the whole Magilla. So make sure, tools are kind of like whatever you prefer to use. We're not dealing with high voltage. Yes, I did have some screwdrivers that had the insulated shafts on them. But then again, we don't deal with high voltage most of the time. Another esoteric thing that I would use is actually the big paper clips. The paper clips I would use were the big ones. And you'll notice a lot of the panels nowadays have the pop-out terminal strips. And you'd go ahead and pop them off. And I'd take the paper clips and stick them in the terminal strips and take my gator clips and clip it onto there. So when you're dealing with a dry circuit, that worked for me really well. The other thing I wanted to say about that is these removable terminal strips can be really dangerous, especially when you're dealing with just a circuit that is utilizing a Class C dry contact, and all you've got is common, normally closed, and normally open. So now if you're gonna monitor this, this is the best way, and the way you should be doing this, especially, particularly if you've got removable terminal strips. Always put your underlying resistor right there. Across the normally closed and the normally open. Put your power onto your common like that. Positive on common. Positive on common would come through here, through your resistor. Your negative would be over here. Now, and let me tell you, I had to do a deposition because somebody did it parallel. Instead of having this lead on the normally closed, they had that lead over on the common. So guess what? When they pulled that terminal strip onto that, that was done. It wasn't going to work, wasn't going to do anything. Sorry. They basically disabled it without notification. This hookup, technicians, is what's going to give you notification if somebody pulls that off of there. So always, when you're using Class C circuits off of a conventional panel or even an addressable panel, that's the way you should wire it. Now, let's get into fire panels. There's two kinds of fire panels. Basically, you have a conventional panel and you have an addressable panel. Now, the conventional panels are classically referred to as FACP, Fire Alarm Control Panel. Been that way for many, many years. A few years back, not longer than me, but yeah, a few years back, they had called fire panels fire alarm control units. But to be honest with you, I never got comfortable with calling a fire alarm a FACU. So it's like, no, I'm going to use FACP. Not too thrilled about FACU. Anyway, FACP, mostly considered conventional. FACU is basically considered an intelligent panel. Now, here's the differences between conventional and addressable. A conventional panel has zones, and a lot of it is, take for example, FCI and Notifier, and a couple of them make this 10-zone panel. So you got 10 initiating circuits. Now, there's pretty much two kinds of initiating circuits. Your first one and most common is going to be a Class B circuit. A Class B circuit is a circuit that goes out and terminates at what is called an EOL, end of line, and it's usually a resistor. Sometimes, very rarely, in the old days, and you might even see an old pyro out there, they actually used a 50 microfarad capacitor as the end of line. But don't be fooled about two-wire circuits, because there's two different types of two-wire circuits. There are two-wire circuits that support a dry contact, normally open, going to a physical short. Doesn't support two-wire smoke detectors. Only specific two-wire circuits are good for two-wire smoke detectors. Give you an example, and I'm going to give you this in Notifier because that's what I work on. Mostly what I work on, although I have worked on FCI, Firelight, Gamewell, Edwards, FCI. In 47 years, technicians, I've worked on frickin' most everything, including nurse calls and apartment access, and you name it, I've probably worked on it because I've worked for security companies and fire alarm companies. But the thing is, an FMM1, which is a notifier, is a two-wire circuit, Class B. It will not support two-wire smoke detectors. It is not designed to do that. Only an FZM1 will support two-wire smoke detectors. Here's the reason for that. It's all got to do with impedance and the balance of the circuit. So if you've got a two-wire circuit, you want to make sure what the rating is for that circuit, if it will support smoke detectors. And if it does support smoke detectors, you need to make absolutely sure that these two-wire detectors are listed for use with your two-wire circuit. And it will tell you how many you can use and what brands you can use on this particular two-wire circuit. Because a lot of these devices, like a two-wire smoke detector, and I've got one here, a two-wire smoke, 2WB system sensor. I got this, and I got wired up for testing. It's a two-wire. You'll notice it's got two black wires, and it does this. Goes in two different directions, goes down the line. You always have to keep that circuit clean and intact. So that's a two-wire smoke detector, and each two-wire smoke detector draws a certain amount of current because it's actually getting its operating power from this two-wire circuit. So just make absolutely sure on a two-wire circuit, regardless if it's an FMM1 like with a notifier addressable or if it's just a conventional two-wire circuit, you know what the specs are. Read the directions. Make sure you read those directions. Now, the other type of circuit, and you don't see this too often, but it is out there, is the Class A circuit. Now, the Class A circuit, and we have it in many government installations that require it to be quote unquote Class A. And we go ahead and do that. Class A circuits. And you can have a Class A circuit on an addressable system too, by the way. You can have a Class A on a conventional or an addressable. And basically what that circuit is it allows you to put these devices, whether they be smokes if it's conventional, or maybe, this is basically here, smokes if it's addressable modules. It allows those devices in case of a broken wire. And that's the whole idea between a Class A circuit. If that wire gets broken somewhere, even if it's both sides of the circuit, doesn't matter. What happens is now the panel switches and puts out circuit on both sides. Now I can draw the circuit out that does this, and it's a little bit complex. In the old days, it used to be just a relay that flipped over and paralleled the one feed side. But anyway, a Class A circuit allows you, even with a open circuit, to still monitor all your initiating devices on the IDC or initiating device circuit. So that's what a Class A circuit is. That's what a Class B circuit is. Remember, there are two different types of Class B, non-2-wire supported and 2-wire supported. So remember that when you're out there in the field, but you make sure what you're dealing with, read the directions. Now, here's what an addressable system, and addressables do have Class Bs on modules, but the circuit in and of itself is an SLC, signal line circuit, signaling line circuit. So anyway, what that is, and I'm going to do that this way this time. What that is a SLC addressable circuit, signaling line circuit. Basically utilizes what they call a star configuration. So what a star configuration is it kind of sounds like it is. It can go all over the place. You can have this thing go here, there, everywhere, all over the place. So let's just draw this out here. And let's say that circuit comes this way in a building. But now you got something over here you want to run into, and you want to wire something up over here. So you come in a junction box and you wire it this way, and you may wire something over here because you're wanting to get into a room somewhere, and you go into that place, and then you may come over here and come over and wire into that. And here comes the fun part. And this is like Rube Goldberg. And if anybody doesn't know what Rube Goldberg is, look it up. It's interesting. Basically, for you that are younger, if you remember Mousetrap, that's kind of, Rube Goldberg was the predecessor to that game, so to speak. But anyway, you come over to here, and you might come out here and do this off of a branch you already did, because with addressable circuits, it doesn't matter because each addressable device has its own supervision. If an addressable device comes offline, it's going to say invalid reply, no answer, whatever. That's what it's going to do. So that's basically called a star configuration. Now, officially, that's what they call it. I like to call it like a tree. You got your main branch coming up, and you could have limbs coming off of here, and those limbs could have twigs, and those twigs can have leaves, and it can be quite complicated. The key factor is, technicians, never exceed the manufacturer's specifications on wire length, wire gauge. Those are important. Never exceed those. And you'll know if you exceed them if you put your oscilloscope at the farthest point of the system. If you put that oscilloscope at the farthest point of the system and your 24 volts is reading 22 volts, technicians, you got a problem. You've used too much wire, or there's a bad resistive connection somewhere, or something's going on. So yes. Now, here's the thing. You can do a Class A on an addressable circuit, but you have to wire a Class A on an addressable circuit just the same way you would do a Class B circuit. The only difference is your end of line is basically 2 terminals in the panel. That's the only difference. With a Class A circuit on an addressable system, you cannot T-tap. You cannot T-tap a Class B circuit because you lose your supervision. You always have to maintain that parallel series path perfectly with no parallel connections. So, some of the other acronyms we use in this industry, besides EOL, end-of-line resistor, FACP, fire alarm control panel, FACU, fire alarm control unit, IDC, indicating device circuit, NAC, notification appliance circuit. Now, NAC circuits also can come in a Class B or a Class A, although normally it's almost always going to be Class B. So the thing about a Class B circuit on a NAC, and let me just straighten up my board here a little bit. The thing about a Class B circuit on a NAC, and I'm going to go ahead and draw this out here. Class B circuit on a NAC is going to have an end-of-line resistor. So it's going to come out, it's going to go out, and you're going to have an end-of-line resistor. And then you're going to have various strobes, horn strobes, and remember, just like a Class B circuit on smoke detectors, do not exceed the rated capacity for that circuit. Do not use the wrong gauge wire. The gauge of wire is very important. The farther you go, the heavier the gauge you need to use. We have rarely used anything less than 16 gauge, and that's on a short circuit. If you're really going out on a fairly good circuit, yeah, you're going to be using 12 gauge wire to get out there. But here's the kicker about an NAC circuit. When it's an alarm, it's positive and negative. But when it's in supervisory mode, it's negative and positive. And that has really messed up some people, especially EC, electrical contractors. When they do some of this stuff, they'll look at this and go, well, there's something wrong with this. The positive's reading negative and the negative's reading positive. What's going on? That's normal. Because that is the way you achieve supervision. Because if you didn't do that, you would be reading through all of these devices. And the reason you would be reading through all these devices, because in this device, there is a diode. Now, a diode is basically a device like a check valve on water. It only allows the power to go one way. So this, when it's hooked up to the circuit, and it's hooked up in here, And you've got this hooked to the red, and you've got this side hooked up to the black. With that diode, it does not allow that which is going to be negative in a supervisory status, in this that's going to be positive in a supervisory status. So it doesn't allow that negative to flow that way. So therefore, this will not mess up the impedance going to this end of line resistor. Now, when it goes into fire alarm and the NAC activates, in alarm condition, this will then become positive. This will then become negative, and it will allow the current to flow through that audible device and cause it to sound and or flash, if it is a horn strobe. So remember, in supervisory condition, it's the opposite polarity. So the red will be negative and the black will be positive in supervision. And it basically flips that polarity when it goes into alarm. So a lot of times on a conventional panel, you will have these as separate circuits. On a NFS 320, which I deal mostly with notifier, but it's going to have 4 NAC circuits on it with end-of-line resistors from the panel. But here's the kicker. When you've got an addressable system, not all of them are going to have onboard NAC circuits, or they're going to have very few. If you got a big building and you could only draw so much power on each circuit, you may not have enough devices. So what's going to happen? You're going to have an RPS, remote power supply, which is classically what an RPS is. Now they come in all kinds of flavors. They come in Notifier, they come in Edwards, they come in Silent Night, FCI, Gamewell, Firelight. A lot of them make these devices, these NAC RPS circuits, NAC devices, which are RPS remote power supplies. So the way they work is they either come off of an FCM1, which is Notifier, which causes it to trigger because it will go on that RPS and say, okay, time to go into fire alarm. Flips the circuit, flips the polarity on the circuit, boom, the RPS goes off. If one of the devices or that RPS goes into trouble, it will open the circuit. Or, alternately, you could actually have a separate circuit and on a separate module, see what the trouble is. Because, and here's the fun part on some of these NAC circuits, it can be very, very interesting. So let's say you do have a NAC circuit at the fire panel. And it is going out in the field for one reason and one reason only, because now synchronization comes into play sometimes with some of this stuff. Now, what we do is we send out a separate synchronization circuit. A lot of times we use modules to cause the RPSs to go off. I've seen this happen before where they will actually take a NAC circuit out to the field, and at the last device, which may be an RPS, they ran the end-of-line resistor in that cabinet. Well, you might have several RPSs because you may have a multi-floor building, and depending on how the architect or whatever decided to make this thing, you basically got feeding in and out of each one of those. And you may even be jumpering each one of these to the synchronization for any strobes you may have. But now if you get an open circuit, you're like, great, I've got 5 RPSs. Which RPS is going into trouble? which can be a real pain if it happens to be an intermittent. Now, with most of these, you can do it separate, and you can have this trigger it, but you'll have an SLC come along through here, and what you'll do is you'll put modules at each RPS and monitor the trouble contacts separately, because then you can just say, okay, this is RPS 1, 2, 3, 4, 5. And when it goes into trouble, it'll tell you, well, RPS 4 went into trouble. And it will also tell you that your circuit went into trouble, because you have to supervise everything. The key factor in life safety is everything is supervised. Any wire that shorts, opens, or grounds has to do something. That's just part of life safety, highly supervised. So that's how NAC circuit works. Now, as far as your initiating device circuit, I mentioned smoke detectors, but there's all kinds of things that can go on a initiating device circuit. There can be duct detectors. Now, some duct detectors are intelligent, some are conventional. The conventional, you got to put a couple modules out there, or one module if you wire it up correctly. But remember, when you wire up a duct detector and you're wiring into it, it's going to have two sets of contacts. It's going to have fire alarm contacts. It's going to have trouble contacts. You must, if you're only using one 2-wire circuit monitor module for a duct detector, you gotta wire the alarm contact first. Alarm contacts always take precedent. So what you're going to do is you're going to make sure you're going to have two sets of contacts on a duct detector. One set of contacts, and this is on a conventional. So one set of contacts is going to have common, normally open, normally closed, and let's call these alarm contacts. And then we're going to have the same thing over here for the trouble. Common, normally open, and normally closed. So you're always going to go to the fire alarm contacts first. So what you do is, just to make sure you have good supervision, is you're going to come in here, going to come over here. Now you're going to come over to there, and you should have a parallel here. So now you'll notice if this goes to a closure, it sets off the fire alarm. If it has a removable terminal strip or a wire comes loose, it is more likely to cause a trouble condition. Remember, when you have two wires, do not twist them together, because if they fall off that terminal, there is no way it's going to go into trouble condition if you twist them together. Twisting wires together in life safety is a quirky no-no. Do not do that. So when this comes over here, now remember, you want this to go to an open, not a short. Okay? So now you're going to pretty much reverse what you did here. You're going to come over, and your end of line resistor will actually be here, because we don't care if that resistor shorts, if that goes into trouble. It doesn't make any difference. It's the circuit we want to go into an open state. So now we're going to go ahead and come over to here. And we're going to take the negative and come over to here. See, now, when this goes into trouble, it's going to short the resistor, but it's going to open the circuit. This way you don't have to use B connectors, wire nuts, whatever. Solder it together with electrical tape, however you do your connections. I like to have as few connections as possible. The more connections there are, the weaker you're going to have a circuit. So in this way, when you do a duct detector, you're going to have it highly supervised. Remember, again, do not twist your wires together. So that'll be great. You do a duct detector that way. Now, same thing on any conventional device that you may have on an addressable system. So if you've got a beam detector that's not intelligent, and they do make intelligent beam detectors. They make beam detectors either point-to-point, separate transmitter and receiver, or they make a beam detector that goes to a bounce-back reflector. They both work on the same principle, occlusion. So you want to make sure your path is clear when you're putting in a beam detector. You want to make sure it's properly aligned. You want to make sure you go by the manufacturer's specifications. I've had balloons and different things trip beam detectors because they partially occluded in such a way they've caused the fire alarm to go off. They will only go into trouble if it's a sudden interruption of the beam. The beam is actually looking for a fluctuating occlusion or a slow occlusion or percentage of occlusion. So you got to be careful with those beam detectors. So ionization detectors, beam detectors, duct detectors. Now ionization detectors, they're going in the way of the beta tapes and the VCR because basically the manufacturers do not want to deal with disposing of them because they are radioactive. Technically, when you have an ionization detector, you are not supposed to throw it away. That is an EPA fine that is enormous for throwing away ionization detectors. They are supposed to be sent back to the manufacturer for proper disposal because they are radioactive. And they started doing that because they realized all these thousands upon thousands of ionization detectors that were going into landfills was actually causing radiation to come up in the groundwater because there were just so many of these devices. That's why they're not making them anymore. It's why they don't want to make them anymore because they don't want to be responsible for getting rid of them. So that about covers mostly this. If you have questions about how something works, what you should be doing with it, how do I do this, that, shoot me a comment. I will try and answer them as best I can. I'm hoping to go ahead and do more of these, more in the future, because I'm now part-time. So I'll have a couple of days a week where I'm free, where I can do more of these. And I do this from my garage. It gets a little bit warm in here. Right now it's not too bad because it's not too bad of a day. But I need to put an air conditioning out here in my studio so I can do these better. If you're enjoying these videos, like, share these videos with people. Again, if you have questions, let me know. I will try and answer them. My next video, I'm going to try and go through the N2 Neuron tester that I was talking about here, which is this tester here. I'm going to go through this. I've got a Silent Night and soon to be coming notifier panel with addressable circuits that I can show you what it looks like. Great thing about these again is you hook them up, you take the chip out, you go ahead and upload it to your laptop into an Excel file, and then you can manipulate it. I'll give you the instructions for that later in my next video. But this is a great meter. It's going to be your oscilloscope, your graphic meter. That's going to do you well. So have a good evening or morning or wherever you happen to be. Thank you for watching, and I look forward to you watching my other videos as they come out. Thank you.